Guys, and welcome back for week 3. This week you are responsible for doing section 3.1, 3.2, 3.3, 3.4, and 3.5. The first thing that we're going to look at is section 3.1, which is defining the derivative. So it's just an extension of what we were doing last week. It is going to be a little bit nicer, I think, than what we were doing last week. And we are going to see more trig come into this chapter. So let's jump in. So section 3.1 starts off with this discussion between the two mathematicians, Sir Isaac Newton and Gottfried Leibniz, who are really the two people who are credited with coming up with calculus. There's kind of an argument as to who did it first. It kind of looks like Newton here on the left probably come up with it first, but it's Leibniz notation that we use today. So a very common argument in the math and physics world there. So the first thing that I want to look at is there's a box here that gives us the definition. Oh, let me bring my, there we go. Now you can see me. So this definition says, let f be a function defined on an interval I containing a. If x is not equal to a is in I, then q equals f of x minus f of a over x minus a is a difference quotient. We have seen this before. We have worked with this before. Here's the more common definition of it. Also, if h does not equal 0 is chosen so that a plus h is in I, then f of a plus h minus f of a over h is the difference quotient with increment h. Again, something that we've talked about. We actually looked at it in several sections in the last chapter. Let's see here. So guys, this is going to go through that discussion of the idea that when you were talking about secant lines, remember, were run through 2 points on your curve or whatever your graph looked like. And then we said, well, what if we take that secant line and we talk about those 2 points being closer and closer and closer and closer and closer and closer and closer until they become just that 1 point, which was the same point. That's when it switched over to be a tangent line. A tangent line only touches a graph in 1 point. So we looked at that definition last time, and here's a bunch of examples of that as we're approaching them coming closer and closer and closer together. So I don't want to spend too much time on that because we really talked about that definition a lot last time. Okay, so here's the idea of limits. Again, this is not a new definition for us. Let f of x be equal to, or let f of x be a function defined in an open interval containing a. The tangent line to f of x at a is the line passing through point a, comma, f of a having the slope of the limit. So we are going to slap a limit on the front of this. Same two definitions. It's just notice how they both have a limit approach or on both of them. And we did talk about how we had to go through and sometimes try to clean those things up. Again, nothing new for us here. So let's go do some examples now. So I want to start with number 3. So number 3 says for the following exercises, use equation 3.1 to find the slope of the secant line between the values of x1 and x2 for each function y equals f of x. So here on, 3 is kind of boring though. Let's do 9. 9 is not as boring. So number 9, we've got f of x equals x raised to the 1/3 plus 1, where x1 is equal to 0, x2 is equal to a. So that's your a and your b values. All right. So the first thing that we really need to do is we need to figure out what y values are associated with each one of these x values. So I want to figure out what's the y coordinate when x is 0, what's the y coordinate when x is 8. And to do that, we actually just plug this into our formula and we work it out. So I'm going to do a new share here. I'm going to share a white screen or whiteboard. And so we're going to have the equation. Write this down for our reference here. You move some boxes. So number 9 we have f of x equals x to the 1/3 plus 1. And then, of course, our first x that we were talking about was 0. Our second x was going to be 8. So what I want to do now is I want to figure out what's the y coordinates associated with each one of these. So to do that, I'm going to plug these in. By the way, guys, if you have forgotten what x to the 1/3 means, x to the 1/3 is actually equivalent to saying the cube root of x. That's just an exponential rule. So really, we could have wrote this the cube root of x plus 1. Doesn't matter. So if I plug in 0, it doesn't matter what I do, the 0 raised to the 1/3, I'm still going to get 0. If I add 1 to it, I am going to get 1. So f of 0 is 1. And then we're going to do the same thing with 8. So f of 8. So if I plug in 8, the cubed root of 8 is 2. And then 2 plus 1 is 3. So this value is going to end up being 3. So really, we've got the point 0, 1. And we've got the point 8, 3. Now, we were asked to find the slope of the tangent line, or excuse me, not the tangent line, the secant line. We were asked to find the slope of the secant line. So now that I have 2 points, it's literally just me going in and using the slope equation. Now, I know they wrote it weird. They had like f of a, or excuse me, f of x minus f of a over x minus a. Woohoo, it's just the slope equation. So here to find the slope of the secant line, remember, I'm going to let this be x1, y1. This is going to be x2, y2. So I'm going to plug it in here. So I'm going to have 3 minus 1 over 8 minus 0. 3 minus 1 is 2. 8 minus 0 is 8. 2 over 8 is equivalent to 1/4 or 0.25, however you want to write it. Cool. So that's just, again, this is something I think we've done a couple of times in the previous section, but there it is again. So let's look at another paragraph in your book here. So I want to go back to page 220. Let me see what 220's got on about it. Okay, so 220, we're talking about the derivative here. So the derivative of a function at a point the top of limit we compute in order to find the slope of the line tangent to a function at a point occurs in many applications across many disciplines. These applications include velocity and acceleration in physics, marginal profit functions in business, and growth rates in biology. This limit occurs so frequently that we actually give it a very special name. We're going to call it the derivative. So the process of finding a derivative is called differentiation. So here is our definition of a derivative. Let f of x be a function defined in an open interval containing a. The derivative of the function f of x at a, denoted by f prime of a, is defined by f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. Or you can do it in terms of limit as h approaches 0 of f of a plus h minus f of a over h.